My name is Chris Athanas. I'm a KMP developer. Tech support has been contacted, but maybe you know somebody at the company to close this portal up, because put in the comments below if you know anybody at the portal company, because these guys, tech support guys, are just doesn't seem to be. Anyway, I'll figure it out. We're going to continue our journey on how to program from the ground up series, and we're going to be getting into the clock. So we were up here in this architecture here, and the clock is out here, and it supplies a little pulse to the MPU. It's part of this control bus, and it's the drum beat. It keeps everything in the CPU in sync. So it basically emits a little short pulse of electricity, a 1, beep, at a regular interval. It goes boop, 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 and it's hooked up directly to the CPU, because the CPU has a control unit that sets everything in motion. It all starts right in there. That's why everything comes into it, out of it. It's like the main part touches everything. Okay, and how does that work? Well, they use this thing called a 555 timer. It's this kind of little chip here, and the reason they call it a 555, I like to know this information, because there's this thing, these 5 kilo ohm resistors inside, that you set this thing up to do all kinds of crazy stuff. And all it is inside it. All it is inside it is a buffer, right? So it contains the last value, and a flip flop, and it just goes bip, bop, bip, bop, bip, flips back and forth, back and forth, back and forth. And this guy goes on to describe it, and there's a bunch of these really fun different types of little kits you can make, little experiments you can make to make a railroad lights to go ding dong, and like police siren, wee woo, wee woo. It's all that stuff. So it's super fun circuit used all over the place, and it's often used inside of computers to do the clock. And there's the 555 chip, and it just says 555. Yeah, and this is got a resistor. So you hook it up with resistors and a capacitor, and it does a certain frequency on and off. Like it'll have dot 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 or dot dot or dot 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 or dee dee. You can set up any of the frequencies for how long it's on, how long it's off, all that stuff. So here we go.
There are a lot of ways to build a clock circuit for our computer, but we want something that's relatively flexible. We can adjust the speed. We don't want it to run too fast. We want to be able to see what's going on.
So adjusting the speed past like what the engineers who designed the computer or whatever, it's called overclocking. Ooh, it's just changing the clock speed. I mean, you can go up to a point, and then there's like the switches, when the switches have to switch. If everything's not all synced up properly, it gets crazy. But you can usually go past, overclock it, and that's but it might get a little too warm.
And so I'm going to use the 555 timer. This is a classic integrated circuit here, the 555 timer, and that's what this chip is here. And so you can tell pin 1 here is by the divot, and 1, 2, 3, 4, 5, 6, 7, 8. And right now I'm powering this with this is just 5 volts coming in from a cell phone charger that I've cut into the USB cable and pulled the 5 volts out. And to power the chip, power comes in 5 volts here on pin 8, and ground to pin 1. You can actually go up to, I think, 17 volts or 16 volts or something with this chip, but 5 volts works. And to control the timing, you've got 2 resistors and a capacitor. And so the first resistor here is going from 5 volts to pin 7. This is a 1K ohm resistor. And then from pin 7 to pin 6, I've got a 100K ohm resistor. And then pin 6 is connected around to pin 2. And then from pin 2 to ground, I've got this capacitor. And this is 1 microfarad capacitor. And you can see the positive side is connected here to pin 2. So the negative side is connected to ground. You want to make sure that's in the right way.
It's important to know what they're talking about when they're talking about a clock. It's just this. It's just something like this.
And so those resistors and the capacitor control the timing. We'll see how that works in a minute. But the output of this chip is on pin 3, and so that's just connected to this LED. And the output can drive a fair amount of current, so we want to make sure we have a current limiting resistor. This is just a 220 ohm resistor here limiting the current through the LED so we don't burn up our LED. So how does it work? Well, a good place to start, of course, is the datasheet. This is the datasheet for the 555.
Okay, let me go into that. You can go watch this detail, but I'm going to get to the end part where he hooks it up here and shows how it operates.
Capacitor from pin 5 to ground to reduce noise.
It's showing the signal
so
here on the oscilloscope.
We see on the scope here, we see this nice transition from 0 volts to 5 volts. But if we zoom in on that, or zoom in, what you see is that nice transition from 0 volts to 5 volts is maybe not so nice. There's a lot of junk in there. So if we add this capacitor that they're recommending from ground to pin 5, boom, clears it right up. So definitely recommend that. 0.01 microfarad capacitor going from pin 5 to ground. There's still some other noise if we go in even further go into, oh, I'm going the wrong way, go all the way into nanosecond range, you see.
So this is why when you overclock it, this is the kind of problems it has, right? So the engineers have seen these issues, right? And they said, okay, for this level, we need to, for everything to settle back down, this time period between here and here, this settling period is really depends on how they've got these circuits all set up. So they've measured it out. It's like, we'll be good here, we'll be guaranteed good here, but what happened? But so the hobbyists and people like just want to go to the edge will go, well, what happens if we push it here? Can we go here? Can we go here? Because does this particular chip that doesn't have the manufacturing defect, can we push it up to here? Nope, they're too far.
There's some overshooting here, and what's happening is when the output wants to turn on, there's a bunch of transistors in here switching and doing whatever they do, and when they switch, there's a different current requirement. So they're pulling more current, or they want to pull more current from the power supply, and they're not able to pull that current as quickly as they would like to, and then at this point they end up getting more current than they wanted, and it kind of overshoots. And I'm surprised we don't see more sort of.
Yeah, so he just goes into details of what can happen when you're overclocking stuff, and then there's the part where he changes the.
What would be really nice is to add change this 100K resistor to a variable resistor, and so I have this 1 mega ohm variable resistor, and you just turn this and get a different resistance, and it goes from 0 ohms, so just a short, all the way through 1 mega ohm, which is 10 times more than this. And so what we can do is we can add this to the circuit here, and what we can do is we can hook that up in place of this 100K resistor. So if I take the 100K resistor out, and what I'll do is just hook up some jumper wires from pins 6 and 7, right? We want to connect between pins 6 and 7. And I'm just sticking it over here with these jumper wires because this is too big to just jam right in there like the little resistor was. But the other thing I'll do is I'll put it, instead of just hooking this variable resistor between pins 6 and 7 by itself, because when you turn it down, it goes down to 0 volts. That would be a direct short between 6 and 7, which would mean that when our clock turns off, the capacitor, instead of discharging like this, the capacitor will discharge almost instantly through here if there's no resistor.
Okay, we keep going.
As a
Wait, what does he change it?
And
he changes it here. Changes the frequency of
the. Oh, there it goes. Yeah, it's just going really slowly. And of course, we can turn this knob and get it to go faster. There, it's going a little bit faster. And we can turn it even more, and it goes even faster. And if we turn it all the way, I don't know if you can see that. I can see it's basically flickering because it's just going so fast. Because right now,
we can't see it on this because it persists the vision of the camera. It blows it away. So
turned all the way down, we just have a 1K resistor. And so when it's charging through 2K of resistors.
All right, so it goes into more how explains how it works, which is super interesting, useful. But the fact that you could just set this thing up and then use a potentiometer to change the clock speed, totally a thing. Back in the early days of the PCs, it had the turbo button. That's all it was doing, was changing the clock speed. That's all it was doing. Okay, let's see what I'm going to talk about here. Okay, so that's the 555 timer. How does it work? Okay, here's the program counter. So this is the thing that keeps track of, right, what is the current address that contains the instruction. Ooh, program counter. Ooh, it's just where it is in memory that's being executed. That's all that's going on there. And it is interesting to see how a program counter is built. And let's listen to our friend Ben again.
So when I build the program counter, I'm going to lay it out physically the same way it is in this diagram.
So this diagram here is just the same thing as this diagram here. Same stuff, except instead of A and B, he's got A and B as X and Y here. Well, same stuff. All right, it's all the same concepts.
And I'm going to put it just above the A register. So I'm going to take my A register. This is the A register, of course. So
this is computer build. And he goes step by step and he shows you how everything is put together here and why this is put together here. And yes, this is the little part that keeps track of the program where the program address is at. This is it. This is all this is.
ALU and the B register. So I'm going to take another breadboard and connect it here above the A register. So take off that strip and connect these here like that. And just above the A register, I'll build our program counter. So we'll start with the 74LS161, which is our 4-bit counter. And then we also have the 74LS245. Which is our tri-state buffers. And so you see that's the same chip we're using for the A register, for the ALU, and the B register.
So we talk about those tri-state buffers. That's that video where it has, it's either to ground or to positive or not connected. So that's the tri-state.
So very similar.
So he goes in here and builds it all up. And step by step shows you where the diagrams were.
The counter out. So this is what takes the contents of the counter and puts it out on the bus.
All it's doing is just counting up.
Yes. So the bus is going to be connected down here on the bottom side of the 74LS245. So let's connect a couple LEDs up just to see what this is outputting. And right now it's disabled, so it shouldn't be outputting anything. And it looks like that is the case. I'll just connect these 4 LEDs. But if we take our counter output enable and we bring that low, we see that the contents of the counter are being put out on the bus. And if we take our counter output enable and take it high, then it's no longer putting that out on the bus. So it looks like the counter out is
so that's
and the
really
counter
all it
enable
is. It's
are
just
both
a
working.
little device that just counts up until it's given another place to start counting and count up again. That's really it. This control unit, this thing right here can tell the program counter to go wherever, to use whatever address. So if you're jumping around and in the program, that's how that works. So yeah, so the next thing is, just look at some of these instructions. So the opcode A9, if you have that A9 hex code in memory, and it gets picked up by the as an instruction, that means load. And in this particular case, load A. So load A means load into this X register, was A, whatever. A, B, X, Y, same thing. Some value from memory. Okay, so there's a whole thing where the CPU will go, get this, fetch this address from memory, and now put it into this other area of memory, my little register, my little area of memory. That's all that is. Move a value from one register to another. So let's say I'm going to move what's in the X into the Y. Okay, or Y to X. Oh, wow. So it's these tiny little moves. Instead of wiring up all these hardware circuits, we're just running these codes, which a lot easier. Now, people used to actually memorize the actual hex codes for this stuff and thought that was programming. It's like, no. We're going to get a mnemonic immediately to represent this stuff. And so there's a store value from a register into the memory. Jump, which just means change the program counter to a new value. Get the instruction. What's the instruction from that new address? Okay. Add with carry. So it goes in here to the ALU, takes the 2 values there, does an add on it, and puts the value in the accumulator register memory and sets some flags. Hey, did I carry or not? Okay. Compare. So you're just taking those 2 values, the 2 values here, comparing them, one greater, one less than is equal to. And then put that in a flag somewhere, and then branch, there's a branch not equal. So if that not equal flag is set, jump over here to this address. That's it. It does this super fast, right? Super duper fast. But it's all this really extremely simplistic stuff. And I'm going to just preview from his computer he built, this little computer from those discrete little logics chips. He's built a computer, and this is the control logic that takes the instruction in, decodes it, figures out what it needs to do, does the thing, gets the next instruction. All right, let's go into it a little bit. We're going to you should watch this whole video. You should actually watch this whole series if you can. If you can watch this whole series, you will do yourself a major favors, because
let's look at how we actually write a program and how a program would actually get executed.
No mysteries.
So I've written a program here that basically says load A 14. And so what that's saying is load the contents of memory address 14 into the A register. And then it's saying add 15. And what that means is add the contents of memory location 15 to the A register and put the result in the A register. And then the last instruction is out. And what that instruction means is take the contents of the A register and output it to the display. Now you might be wondering, where do these commands come from? How do we, why does load A14 mean that? And this is actually a really cool thing, is we're building this computer ourselves, and so we get to define what the language is. We get to define what these commands are. So I made these up. And
as did the original people who made these original machines. They just made stuff up that was just a representation of the set of instructions, a set of commands. That's all this is. It's not mystery. It's nothing magic. This arrangement of circuits has no idea that we've actually named these things. It just sees it as there's a line here, signal says go here now. That's all it does. It has no idea about any of this stuff.
Really, we can come up with any commands that we want, as long as it's some operation that we can actually do with this computer, and we can call them whatever we want, and we can come up with whatever we want. So this is just what I've come up with, is this load A command, and I've decided that what that means is it means to take whatever's in the location that's referred to in memory and put it into the A register. And then I've decided that this add command, what it means is take whatever's in this location and add it to the A register and leave the content
what it represents.
in the A register. And then the output command, of course, just means take whatever's in the A register and output it. And so we could come up with whatever commands we want.
And output, input, it's all just our minds around it. It's just putting electricity on these lines in some way that's completely logic based.
If we wanted to subtract, we can do that. The computer knows how to subtract. If we want to move things into the B register, we could have a command that does that. Anything that we can do with this computer, we can make a command to do that. So then how do we actually program these things into the computer? So for that, we want to put these instructions in memory because the computer can execute programs from memory. And again, we're making the computer, we can make whatever choices we want to make here, but what I think makes sense is for the first instruction to go at memory location 0, and then the next instruction to go in location 1, and then the last instruction here to go in location 2. That seems to make the most sense, just start at 0, 1, 2. So the memory locations for these are going to be 0, 0, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. So that's where in memory these commands are going to go. But how do we actually put this command load A14 into memory location 0? Because load A that's not a, this is an 8-bit value. Load LDA or load A is sort of a mnemonic word. And so again, since we're building the computer, we get to make the decision here of what this actually is represented as in binary. So since we get to make up this command, we also get to make up what value it corresponds to. So I'm going to say LDA corresponds to 0001. That's LDA. And then
so command number 0001 is LDA. Arbitrarily, it could have been 1010. It's completely arbitrary.
And so that'll be the first 4 bits. And then the next 4 bits of the command are going to be the actual memory location that we're loading from. And so in this case, 14. And so 14 in binary is 1110.
Okay, so this is a very special case because it's a small computer and it's just thing. So in this particular instance, the memory location contains the command and the parameter. Most my computers just has a command, and the next memory address will be the parameters, or 2 parameters, or 3, or whatever. 4 or whatever. But in his computer, to keep it simple, he's got the instruction over here being 4 bits and what the parameter is being 4 bits. It's very basic.
This LDA 14 command.
But still, this is exactly the same exact thing that's happening in all modern computers.
Actually going to put it into memory as 00011110. And that corresponds to load A 14. And again, we're just making this up. I could have used any 4-bit value as long as I'm consistent with that value, meaning load A. So same thing with add. Of course, I can't use 0001 for add. I've got to use something different. So I'll just use 0010. I'll just use 2. And so that'll be the binary representation of add. And of course, along with the add instruction, we've got to tell it what address to add the contents from. And so that's 15, which is just all ones. And then output. Again, this is a new command. We get to decide what the representation is. I could go with 3, or I could go with anything I want. I could just go 1110. And I think that'll be what our output is. And in this case, output, I'm going to say this command says take whatever's in the A register and output it to the output display. And so I don't really need to tell it anything else here. So the other 4 bits could be anything that we choose. So we'll just set them all to 0. And you'll see when we actually build this output command in the logic here, we'll just ignore, we won't use those 4 bits for anything. So they could really be anything. But of course, you could imagine having a command that says like output from memory and then a memory address, and it would go fetch the contents of that memory and output it. You could very easily define a command, but we're not going to do that just yet. So this will be the program that we try to program in here. And so we can program it just by setting those values into memory. So what does that mean? So if we want to be in programming mode here, we go to address 0, and so we're at address 0, and we want to set this 0001 1110. So 0001 1110.
So this is how this particular process you're seeing right here was how the original programs were actually keyed in to a system. Before they had keyboards and a little bit higher level processing, they were doing it like this. Brutal. Talk about debugging problems.
And we'll program that in.
If you just get one of these wrong, the whole thing doesn't work.
Now at address 0, we've got that command. So then we'll go to address 1 here, and then we'll put in this. So 0010 1111. And we'll program that. So now we have our second command.
But still, going through all this hassle, it was better than writing and doing these calculations by hand. Yes, for sure. Because you couldn't train up 1,000 people to do 1,000 equations every single day, all day long, 8 hours a day. But you can make this machine do it. So that's why we suffered through this.
In memory. And then we'll go to address 2, our last command. Oops. And program in our output command. So that's just 1110, and then actually the rest don't matter, but I'll set them all to zeros and program that. So that's our output command. So now we've actually programmed our computer. We put the program in the computer. Of course, it's not going to work because we don't have any control logic yet, but we can start to step through and see how this might actually work once we build the control logic, so we get a sense of what the control logic needs to do. And of course, for this program to make sense, what we're saying is that we're loading the contents of memory location 14 and we're adding to it the contents of 15 and we're outputting that. So we need to put some data in address 14 and 15. So if I go to 14, it's got some data here. Let me put some other data. So if we just go here to address location 14, which is 1110, and 15, which is 1111, I'm going to put some data here. Let's say 000111100. And in this location, we'll say 0001110. And this, if we convert it to decimal, is 28, and this is 14. And so what this program's really good.
So he's programming the data that this address points to, right? And it points to address 14. This one points to address 15. Okay, cool.
What it is, it's going to say load whatever's in memory location 14, which is the number 28, into the A register. Add
a pointer. Ooh, pointers. Wow. They make a big deal about these pointer things, but that's all it is.
Whatever's in 15, so it's going to add 14 to that, and then it's going to output whatever the sum of those two numbers is. So we're 14, so I'll program in the first number, and then we'll go to 15 and program in the next number. So we got 14 and 15. And if we go back to 0, we've got our first command there. And so I'll switch this back to program, so the memory address is no longer controlled by the dip switches, it's controlled by the memory address register.
Now, on the older machines, they weren't putting the computer using these dip switches to put the data in. Now, some people did in the microcomputer, but in the early big machine areas, that's what they're using those cards for. And that had the punch holes in. So instead of people typing in, or they were just trusting people punched the holes correctly, and then it was read completely without human intervention.
So now we've got this program programmed in here, and obviously it's not doing anything, but of course there's no control logic, so it wouldn't do anything. If we had the control logic built already, then the program would run, but that's obviously not happening. So we need to kind of step through this step by step, and I need to essentially manipulate these control lines to do what the control logic would do if it were built, and that way that should help you understand what it is we're actually trying to do when we build the control logic. So to step through step by step, I'm going to stop the clock, and we can still step the clock manually by pushing this button, and so we're going to go super slow through this and go step by step. So the first thing that's going to happen when we start to execute a program, or really anytime we start to execute a command, is we need to load the command from memory and put it in the instruction register, because the instruction register is what tells us what command we're currently running. And so the beginning of executing any command is a fetch cycle, where we fetch the instruction from memory and put it into the instruction register. Now the other component that comes into play here is the program counter, which is up here, because the program counter is going to count through which instruction we're on. And it starts at 0, which is where it is right now. But once we execute the first instruction, it's going to go to 1 and then 2, and then we keep going 3, 4, 5, and so forth until we stopped executing our program. So our program counter is at 0, which is where we want to start. And the first instruction that we want to fetch from memory is in memory location 0. But in order to get to memory location 0, of course, we're already there, but we're just sort of there by accident. Really, to get there, what we need to do is we need to take the program counter, the contents of the program counter, which is 0 in this case, but as we get to the next instruction, you'll see it's 1 or 2. We need to take the program counter and move that value into the memory address register here. So what we're going to do is we're going to say program counter out, so counter out, which is here, and then memory address register in, which is over here. So this is saying take the program counter.
So he's doing, by manipulating these wires here, he is actually simulating what the control unit that he's about to build over here, we will build, is doing. So he's doing the little microcode steps at the control, where the this is simulating the control unit, taking, okay, well, I got stuff from here and put it here. I got stuff from here and put it here. Stuff from here and put it here. I'm going to ask this thing to do its thing, and then I'm going to take the result, put it here. That's what so this is what he's doing with this down here. And he will build this device, but this is so great to see exactly what the conceptualization of what's going on is, because yeah, when someone just blasts you with, we'll just put a control unit. Well, what is that thing doing? Oh, this is what it's doing.
And put its value onto the bus. And so there's a 0 on the bus. There's a 0 here. This is not going to look very interesting. There's a 0 in the program counter. There's now a 0 on the bus. And then we're going to take the 0 from the bus and put it into the memory address register. And so all of that's going to happen on the next clock pulse. So there's the clock pulse. And yeah, that 0 just went over there. I'm not sure if you saw it, but no, that 0 went over there. It'll be more interesting for the next instruction.
He's so funny.
Trust me. So the first thing we did, so if we're executing this LDA, which is load A 14. That's the first instruction we're executing. The first thing we did is we said program counter out and memory address register in. And then we pulse the clock. So this is the first thing we did. The next thing we're going to do is we want to take the contents of memory. So now that this is pointing at 0, of course it was before, but just bear with me. This is now pointing at address 0. So what we're seeing here is the contents of address 0, which is this here, the 0001110, which is the load A14. So this is the load A14 command. We need to move that to the instruction.
So this is called microcode. So each opcode, this is why it takes a couple cycles to have a CPU actually run an instruction, because this is the microcode. There's like little programs that run for this LDA. There's a little program that runs in the control unit to do what LDA does. It just doesn't do one thing. It could do a whole bunch of things. It could do a whole bunch of things. It could take 10 clock cycles, 2, 5, 8. It depends on what you're doing, right?
Register. And so to do that, what we want to do is turn all these things off. And so for the next clock cycle, we want to take the RAM out, which is this here. So RAM out, and you can see the contents of RAM is now on the bus. And then we want to say instruction register in, which is right here. So we're going to say instruction register in. And of course, nothing happens yet until the clock pulse, which is good because that gives us time to set up and change what's going on in the control logic here before the next clock pulse.
So he's showing the microcode instructions. This is so cool. No, I've never had a teacher, an instructor even understand what was happening here, but he's breaking it down. It's like, it's not that difficult. It's just a program within a program. Oh, okay.
The next clock pulse here, and there it goes from the RAM into the instruction register. And so you can see I actually use different color LEDs here. So the blue indicates the instruction. So LDA is load A, and so 0001 corresponds to that. So you can see that. And then the yellow is kind of the operand, the 14. So now that we've loaded the instruction, so the next thing we did here, right, was RAM out, and instruction register in.
So he's simulating reading this instruction, whatever this instruction is. Oh, okay, it's load A14. And then he's doing the microcode. So cute.
This was the next set of signals that we did for the next clock pulse. And then the last thing we want to do as part of the fetch cycle is actually increment the program counter so that the next time through, the program counter is pointing to the next instruction we want to load. So we'll turn off these signals. And now we just want the counter enable signal to be high or active. So counter enable is active. And so now in the next clock cycle, the program counter will increment. And so there it goes, it increments to 1. And so that's going to stay there in the program counter just to keep track of where we are in our program so that the next instruction we execute will be fetched from memory location 1. So now we can set that low. So that was counter enable, which increments the program counter. So these are the 3 steps we've done so far. We've moved the address from the program counter to the memory address register. We've loaded the instruction from RAM into the instruction register, and we've incremented the program counter. And we're going to do that for every instruction that we execute. So when we build the control logic, it's going to have to kind of know how to do this. Once we've done this, the next thing that we're going to do is actually execute the instruction. So now we've got the instruction. The control logic can look in the instruction register and see, okay, the instruction is 0001. What does that mean? Well, that means load A. And so the logic that we build here is going to have to take that into account and know what to do with load A. Well, we've decided that load A means take the contents of memory address whatever this is 14 in this case, and put that memory into the A register. So the first thing we've got to do is actually get the memory address register pointing at 14. So to do that, we want to take the contents of the instruction register, or really just the lower 4 bits, which is actually the only part of the instruction register that's hooked up for output to the bus. So if we do instruction register out, if we enable that signal, you'll see only the lower 4 bits actually go out on the bus. The top 4 bits stay all zeros, and that's just because we've only hooked up those 4 signals. And so now what we can do is we can take those lower 4 bits and read that into the memory address register. So if we say memory address register in, so we've got instruction register out and memory address register in.
So this is a 4-bit computer. It's like a half the size of a microcomputer, but still, everything he's doing is exactly the same. It's just scaled up 2 times for a microcomputer.
Now, if we do that and then do a clock cycle, when that clock goes high, that address goes into the memory address register. And when that happens, we're now pointing our memory at location 14. And that's the value that we want to put into the A register. And so the next thing we'll do is take the contents of RAM. So we'll say RAM out, put that on the bus. So now that's on the bus. And we want to put that in the A register. So we're going to say RAM out and A register in. And so the A register in, we'll set that. And so now with that set, A in, on the next clock cycle, this value will go into the A register. And there it is. And with that, we have actually executed this load A14 operation. So the opcode, LDA, load A, and the operand 14, memory location 14. We have loaded the contents of memory location 14 into the A register. And we just had to follow this. And so when we actually build the logic that does this, instead of us fiddling around with the signals for each step, we'll build logic that knows what those signals are. And so with that, we can move on to the next instruction, which is add 15.
So let's watch the rest of that. That's how it works. So the fetch, decode, recycle, and you just talked through about that. It fetches, it decodes the instruction register, it decodes it to see what the operation is, it actually does the operation, executes it, and then after it's complete, it updates the program counter. Jump instructions. If that's what we just looked at. Super cool, like really useful. Here's a register. So when you're pushing, it's just a little piece of memory, just a little super fast piece of memory because it doesn't have to go on a bus anywhere. Doesn't deal with bus contention. It's like right there just for one thing only. That's the only thing it's for. That's why it's super fast. And it's right next to these operations. So you don't have to go anywhere for it. So as well as the other registers, the stack pointer is another one for doing subroutines, which we'll talk about. Program counter, instruction register, the memory address register, the X and Y or the A and B. Like some use it X and Y, some use A and B as the 2 things that are going to go into the ALU. Some will have multiple ALUs. Some have multiple of all these things. But this is the basic fundamentals that they're all going to copy and extend and change. So so here's the comparison registers. There's a 0 flag. It's just a bit. It says, okay, the last operation we compared 2 things together, it was 0 or equal or greater than, less than, or negative, or there was a carry bit if you went through adding a bunch of stuff up. So yeah, that's it. And then here's the control unit, which Ben was just simulating. He actually shows how an adder circuit. I'm not going to go into that. You can watch this thing about how things in the ALU does all those operations. It's the same kind of stuff. It's like, oh, this is a clever way of dealing with this. So you can go watch that video because it's quite good. Well, it's the same kind of stuff. It's just like, okay, I'm gonna do this now. I'm gonna do this. Okay, this turns out this does this. Okay, more of that kind of stuff. And the control unit. So Ben was doing the simulation of the control unit when it took an instruction and does the microcode. He was doing all the microcode steps. Step up, push this there, push that there, push that. All the little steps like the control unit does. That's what the control unit is. It's the part of the CPU that does the fetching from the memory, decoding what the instruction is, and then doing the stuff in the instruction, and then going to the next one. And here's an example of basically another thing where this is another machine language program. It's actually machine and assembly at the same time because we got the mnemonic over here for the assembly language codes, but it would actually look like this in memory. Like he just programmed in those little dip switches. Here they are, A905, 8D000. These are just in memory. And the program counter gets to this point, reads these instructions and says, oh, it means store A in memory location 0. And then store A in memory location 1. And then this is like adds things together. And that's basically, this program just adds two numbers together. And the result is 12 at OXC. Yep, that's how that works. And that's about half an hour. Yep. And so we're going to get into assembly language, which is just those mnemonics, but in every different opcode is going to have a slightly different value depending on what it's doing with the different parameters. And assembly language, abstracts all that away. So all you have to say is load. I don't know which exact opcode you're going to need for this, but I want to load A to B. To whatever the opcode is for this processor, just give that to me. So it just abstracted away this need to know the opcodes. And now we're going a little more high level. We're not thinking about circuits anymore. We're thinking about more like structures and how things are laid out and more conceptual ideas. And so we'll get into the machine assembly language, which is just kind of like conceptually what we're doing with the machine language. It's going to we're trying to pop one level up. All right, we'll continue that in the next one. Thanks for watching. Give me a thumbs up and like and subscribe and all that.